You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Resilience engineering in cloud environments recognizes that failure is inevitable and focuses instead on designing systems that can withstand, recover, and adapt under stress. The purpose of resilience engineering is to proactively ensure that acceptable service levels are sustained even when components break, networks falter, or workloads spike unexpectedly. Unlike traditional approaches that aim for flawless prevention, resilience assumes imperfection and prioritizes graceful degradation and rapid recovery. This mindset changes how architects, developers, and operators build and operate services, emphasizing redundancy, automation, and testing under adverse conditions. For learners, resilience engineering is about shifting from a fragile stance, where unexpected faults lead to outages, toward robust designs that anticipate uncertainty, absorb shocks, and continue to deliver critical functions reliably. It bridges the gap between reliability theory and practical operations, ensuring systems can thrive in imperfect real-world conditions. At its core, resilience engineering is not about eliminating every possible failure, but about designing systems to degrade gracefully and recover quickly. Perfect prevention is unattainable in complex distributed systems, where countless variables can trigger faults. Instead, the goal is to minimize the impact of those faults on users and business outcomes. Graceful degradation ensures that non-critical features may fail without affecting essential functions. Rapid recovery restores normal operations swiftly, minimizing downtime and user frustration. For example, an e-commerce site under database stress may disable recommendation features but still process core transactions. By adopting this perspective, resilience engineering balances realism and effectiveness, acknowledging that failures will occur but ensuring they do not escalate into catastrophic service disruptions. Reliability is the probability that a system will perform correctly over time, and it complements availability as a key measure of resilience. Availability describes whether a service is operational at a given moment, while reliability measures the likelihood of correct performance over an extended period. A system with high availability but low reliability may be up frequently, but fail often in subtle ways, such as returning errors or inconsistent data. Reliability is strengthened through redundancy, fault tolerance, and monitoring, ensuring not just uptime but correct outcomes. For example, a replicated database may be available even during node failures, preserving reliability by maintaining consistent reads and writes. By distinguishing reliability from availability, resilience engineering ensures that systems are not merely accessible but dependable in practice. Service-level objectives and service-level indicators provide the framework for measuring and managing resilience. SLIs are the metrics that capture service health, such as request success rate, error percentage, or response latency. SLOs define the targets that services must meet, such as maintaining 99.9% request success over a rolling period. Together, they create clear expectations for both engineers and stakeholders. For example, an SLO might commit to 200 millisecond response times for 95% of user requests. These targets shape engineering priorities, incident response, and change management. By explicitly defining how reliability is measured and what levels are acceptable, organizations avoid vague promises and instead align technical resilience with business commitments. Error budgets introduce an innovative way to balance reliability with delivery speed. An error budget defines how much unreliability is permissible within an SLO, providing a buffer for failures. For instance, if an SLO requires 99.9% availability, the error budget allows 0.1% downtime or errors within the period. This budget informs decision-making. If the budget is underused, teams can deploy new features aggressively. If it is exhausted, deployments may be slowed to preserve reliability. Error budgets prevent teams from over-engineering or under-delivering, striking a balance between innovation and stability. They also reframe outages not as absolute failures but as expected, budgeted occurrences that must be managed responsibly. Health checks form the foundation for automated recovery and safe rollout. Readiness checks confirm whether an application is prepared to handle traffic, while liveness checks determine if it is still functioning correctly. Platforms such as Kubernetes use these checks to route traffic only to healthy pods and restart those that fail. For example, if a web service passes readiness but fails liveness, it may be removed from load balancing while being restarted. Health checks enable automation to replace manual monitoring, ensuring that unhealthy components are quickly identified and recovered. By embedding these checks into deployment pipelines, organizations increase both safety and speed, rolling out changes with confidence that faulty versions will be caught and corrected automatically. Auto-scaling policies allow systems to adapt capacity dynamically in response to demand. These policies monitor metrics such as CPU usage, request rates, or queue lengths to decide when to add or remove resources. Scaling out prevents overload during peaks, while scaling in reduces cost during lulls. Policies can be reactive, adjusting to observed metrics, or proactive, based on schedules or predictive analytics. For instance, an e-commerce platform may scale web servers horizontally during holiday sales and contract afterward. Auto-scaling ensures that resources are aligned with demand, preserving both performance and efficiency. It turns elasticity into a resilience mechanism, ensuring that systems remain responsive even under unpredictable workloads. Horizontal and vertical scaling represent two approaches to expanding capacity. Horizontal scaling adds instances, distributing load across more servers or containers. Vertical scaling increases the power of individual instances by adding CPU, memory, or storage. Each has trade-offs. Horizontal scaling offers better fault tolerance and flexibility, while vertical scaling may be simpler but limited by physical or virtual resource ceilings. For example, a web tier may scale horizontally with multiple stateless instances, while a database may scale vertically to handle larger workloads on a single node. Resilience engineering often favors horizontal scaling for its redundancy benefits, but both approaches remain valuable tools in the scaling toolkit. Self-healing mechanisms automatically restore systems to their desired state without manual intervention. This includes restarting crashed processes, replacing unhealthy nodes, or reconciling infrastructure drift. Orchestration platforms like Kubernetes exemplify self-healing by continuously monitoring workloads and rescheduling them on healthy nodes if failures occur. For instance, if a container crashes repeatedly, the orchestrator replaces it without human involvement. Self-healing reduces mean time to recovery dramatically, ensuring that small failures never escalate into large outages. It shifts resilience from reactive human response to proactive automation, embedding recovery into the system itself. Idempotency ensures that retries during transient failures do not create unintended side effects. In distributed systems, operations often fail due to network glitches or temporary overloads, requiring retries. Without idempotency, retries can duplicate actions, such as processing a payment twice. Idempotent design ensures that repeating the same request produces the same outcome without harmful duplication. For example, using unique transaction IDs allows payment systems to recognize and discard duplicate retries. Idempotency aligns resilience with correctness, preventing error recovery mechanisms from introducing new problems. It reflects the principle that resilience is not just about availability, but about preserving integrity under stress. Backoff and jitter strategies prevent retry storms that can overwhelm downstream services. When clients retry failed requests too aggressively, they can magnify outages rather than resolve them. Backoff introduces increasing delays between retries, while jitter adds randomness to prevent synchronized surges. For example, exponential backoff with jitter ensures that retries are spread out and staggered, reducing pressure on recovering services. These strategies protect systems from cascading failures and allow time for faults to clear. They demonstrate how resilience includes not just recovery but moderation, ensuring that corrective actions do not themselves become destabilizing. Circuit breakers provide another safeguard against cascading failures by halting calls to unhealthy services after repeated errors. Once tripped, the circuit breaker blocks further attempts until the service shows signs of recovery. This prevents clients from continually stressing a failing service, giving it room to recover. For example, if a downstream API is consistently returning errors, a circuit breaker can stop requests temporarily and fail fast instead of compounding delays. Circuit breakers embody the principle of graceful degradation, isolating faults and preventing them from spreading through the system. They allow resilience to be engineered into interactions, not just individual components. Bulkheads apply the maritime metaphor of compartmentalization to distributed systems, isolating resources so that faults remain contained. For example, thread pools or connection limits prevent a single workload from consuming all available capacity, leaving other services unaffected. By creating boundaries, bulkheads ensure that localized failures do not escalate into systemic outages. For instance, if one microservice experiences runaway requests, bulkhead isolation prevents it from starving others of CPU or memory. This design reduces coupling and preserves resilience by ensuring that faults remain confined. Bulkheads represent one of the simplest yet most powerful strategies for preventing cascading failure. Queue-based decoupling smooths traffic between producers and consumers, buffering bursts and insulating services from variable rates. Message queues absorb surges, allowing downstream services to process at their own pace. For example, an order processing system may queue incoming requests during peak load, ensuring that transactions are eventually processed even if delayed. Queues add resilience by reducing dependencies on synchronous availability, turning hard failures into temporary backlogs. They also enable retries and reprocessing without losing data. Queue-based decoupling embodies resilience as elasticity, ensuring that systems flex under pressure rather than breaking outright. Graceful degradation preserves user experience by maintaining essential functions even when systems are stressed. Instead of failing completely, services disable non-critical features to conserve resources. For example, a streaming service may reduce video quality under heavy load while keeping playback continuous. Graceful degradation transforms outages into reduced performance, preserving business value and customer trust. It demonstrates how resilience is not binary but graduated, ensuring that systems deliver the most important outcomes under duress. This practice aligns engineering priorities with user expectations, focusing resources where they matter most during failure. Dependency mapping identifies the critical upstream services on which systems rely, providing the blueprint for resilience engineering. By cataloging which components are essential and which are optional, organizations can prioritize protections and mitigation strategies. For example, mapping may reveal that authentication services are mission-critical, requiring redundancy, while recommendation engines are less essential. Dependency maps also highlight hidden couplings that may propagate failures unexpectedly. By making dependencies explicit, resilience engineering ensures that protections are aligned with actual business priorities rather than assumptions. This knowledge informs scaling, redundancy, and chaos testing strategies, creating a foundation for engineered resilience. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Chaos engineering is the practice of deliberately introducing controlled faults into systems to test their ability to withstand and recover from disruptions. Instead of assuming resilience, teams validate it under real-world stressors. Chaos experiments might involve terminating instances, severing network connections, or corrupting dependencies, all under carefully monitored conditions. The goal is to reveal hidden weaknesses before they surface in production incidents. For example, terminating a random instance in a cluster tests whether autoscaling and load balancing respond correctly. Chaos engineering shifts resilience from theory to evidence, ensuring that recovery mechanisms are not just designed but proven. By embedding chaos experiments into routine operations, Organizations cultivate confidence that their systems can survive turbulence without collapsing. Fault injection extends chaos engineering by simulating specific failure modes such as latency, packet loss, or resource exhaustion. Tools can deliberately delay responses, drop network packets, or saturate CPU and memory, observing how services react. For instance, injecting latency between microservices can test whether timeouts and retries behave as expected, preventing cascading slowdowns. Resource exhaustion scenarios may reveal whether auto-scaling policies kick in or whether applications fail under load. Fault injection creates a safe laboratory for testing resilience at scale, validating that back-off, circuit breakers, and bulkheads operate effectively. By confronting systems with realistic stressors, teams can refine designs and ensure that mitigation strategies hold under genuine conditions, not just in assumptions. Game days turn chaos and fault injection into structured exercises, where teams rehearse incident scenarios as if they were real. These scheduled events involve role-playing outages, activating incident response procedures, and executing runbooks. For example, a game day may simulate a regional outage, testing whether failover occurs seamlessly and whether communication protocols function effectively. Game days also evaluate human factors, ensuring that responders know their roles and can coordinate under pressure. The goal is to surface gaps in preparedness, whether technical, procedural, or organizational. By practicing failures in safe but realistic ways, game days transform resilience from an abstract goal into a lived discipline, building confidence and muscle memory for real incidents. Multi-availability zone design reduces single points of failure by spreading components across isolated failure domains within a region. Cloud providers engineer zones to be physically and logically separate, with independent power, networking, and cooling. Deploying services across zones ensures that a failure in one does not incapacitate the entire application. For example, databases can replicate synchronously across zones, while stateless services are balanced across multiple zones by load balancers. Multi-AZ architecture is often the first step in resilience, providing local redundancy without requiring global distribution. It demonstrates how resilience can be achieved incrementally, starting with fault isolation at the regional level before expanding to cross-region strategies. Multi-region strategies extend resilience further, addressing the possibility of entire regional outages. Active-active models run workloads in multiple regions simultaneously, distributing traffic and providing seamless failover. Active-passive models keep one region on standby, ready to take over if the primary fails. Each approach has trade-offs. Active-active maximizes availability but increases complexity, while active-passive is simpler but may involve longer failover times. For example, a global e-commerce platform might operate in 3 regions, steering users to the closest but capable of shifting traffic instantly if one goes offline. Multi-region resilience transforms outages from catastrophic events into manageable transitions, ensuring continuity even during large-scale disruptions. State management is critical to resilience because distributed systems must remain consistent under failure. Techniques such as replication, quorum, and leader election preserve data integrity and service availability. For instance, a database cluster may require a majority quorum to accept writes, ensuring that no split-brain conditions occur during failover. Leader election algorithms determine which node coordinates updates, maintaining order in dynamic environments. These mechanisms ensure that services continue to function predictably, even when nodes fail or partitions occur. State management underscores the reality that resilience is not just about keeping systems running, but about keeping them correct and coherent under stress. Data resilience focuses on preserving information with replication strategies aligned to recovery point objectives. Synchronous replication ensures that data is committed in multiple locations before confirming success, minimizing data loss but adding latency. Asynchronous replication reduces latency, but risks losing recent transactions during failures. For example, financial systems may require synchronous replication across zones, while analytics workloads tolerate asynchronous replication across regions. By aligning replication models with business requirements, organizations balance performance with assurance. Data resilience ensures that recovery restores not just service availability but also data integrity, which is often the most critical aspect of continuity. Traffic steering and DNS failover provide mechanisms for redirecting users to healthy endpoints during disruptions. Load balancers can reroute traffic automatically when services fail, while DNS can shift queries to alternate regions or providers. For example, if a region becomes unreachable, DNS health checks can update records to point clients to a standby region within minutes. Traffic steering also enables granular control, such as sending a fraction of traffic to a recovering service to test stability. These controls ensure that resilience is not only about back-end recovery, but also about directing users seamlessly to functioning endpoints, preserving experience and business continuity. Capacity headroom is the deliberate reservation of spare resources to absorb failover surges and seasonal peaks. Without headroom, scaling policies may struggle to cope with sudden demand or redirected traffic during outages. For example, if a region fails, remaining regions must have capacity to handle doubled load instantly. Headroom can also address predictable events, such as holiday shopping or product launches where demand temporarily exceeds normal baselines. While unused capacity incurs cost, it represents insurance against degraded service under stress. Capacity headroom illustrates the trade-offs inherent in resilience. Investing resources now to reduce the risk of failure later. Observability of resilience depends on monitoring the golden signals of latency, traffic, errors, and saturation. These metrics provide a holistic picture of system health under stress. Latency reveals how quickly services respond, traffic shows demand patterns, errors indicate correctness, and saturation reflects resource constraints. For example, rising latency and error rates may signal bottlenecks even before full outages occur. By focusing on these signals, teams can detect degradation early, intervene proactively, and validate whether resilience mechanisms are functioning. Observability transforms resilience from a theoretical property into a measurable reality, ensuring that protections are not only designed but continuously verified in operation. Runbooks codify the steps required for failover, rollback, and verification, providing a structured response to incidents. Automated execution, where possible, ensures consistency and reduces reliance on human memory under stress. For instance, a runbook may describe how to promote a standby database to leader, update DNS records, and validate replication integrity. By documenting these steps, organizations reduce mean time to recovery and ensure that even less experienced responders can act effectively. Runbooks also serve as training tools, supporting game days and chaos exercises. They transform resilience from an ad hoc response into a disciplined, repeatable process. Change safety practices limit the blast radius of deployments by introducing new code or features gradually. Canary releases expose a small percentage of users to changes before full rollout, enabling detection of problems early. Feature flags allow functionality to be toggled on or off instantly without redeployment. Staged rollouts spread changes over time, reducing the risk of widespread disruption. For example, a canary release may reveal that a new feature increases error rates, allowing rollback before all users are affected. Change safety practices align resilience with innovation, ensuring that the pursuit of new capabilities does not compromise stability. Cost-risk trade-offs recognize that resilience is not free. Redundancy, replication, and capacity reserves all incur expense, and organizations must balance these against acceptable impact. For instance, multi-region active-active deployments maximize continuity but may be excessive for low-priority workloads. Documenting trade-offs ensures that resilience investments align with business value, making clear where performance and cost intersect with acceptable downtime or data loss. Cost-risk analysis prevents over-engineering while ensuring that critical services receive the protection they need. It reframes resilience as a business decision, not merely a technical one, aligning engineering with organizational priorities. Evidence collection captures the results of resilience exercises, including metrics like mean time to recover, test outcomes, and remediation of findings. By recording evidence, organizations demonstrate to stakeholders, auditors, and regulators that resilience is actively managed and continuously improved. For example, after a game day exercise, evidence may show that failover completed in 4 minutes, exceeding SLOs, but also reveal communication gaps that require remediation. Evidence transforms resilience from an aspirational quality into a documented, verifiable practice. It closes the loop between planning, execution, and assurance, ensuring that lessons learned translate into tangible improvements. For exam purposes, resilience engineering focuses on selecting appropriate scaling policies, automated self-healing, and chaos techniques aligned with SLOs and risk appetite. Candidates should be able to distinguish between horizontal and vertical scaling, explain retry strategies like back-off and jitter, and apply concepts like circuit breakers and bulkheads. They should also understand how chaos engineering, multi-region designs, and observability contribute to resilience. Exam questions may test knowledge of balancing cost against risk or of documenting evidence for continuous improvement. The emphasis is on recognizing resilience not as a single tool, but as an integrated practice combining automation, measurement, and proactive testing. In summary, resilience engineering ensures dependable service delivery by embracing failure as a design condition rather than an exception. Auto-scaling policies adjust capacity dynamically, self-healing mechanisms restore health automatically, and chaos experiments validate recovery assumptions under controlled stress. Multi-zone and multi-region designs spread risk, while state management and data replication preserve integrity. Observability and runbooks ensure that resilience is measurable and actionable, while cost-risk trade-offs keep it aligned with business priorities. By rehearsing failures and collecting evidence, organizations turn resilience from a reactive hope into an engineered property. The outcome is cloud services that remain trustworthy and stable under the messy, unpredictable conditions of the real world. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.